Hello and welcome to A Theory of Everything. I'm Luis Razo, the director of EISM and host of the channel. Today we have the pleasure of talking to Professor Eliahu Cohen, a theoretical physicist and quantum engineer at the Alexander Kofkin Faculty of Engineering at Bar Ilan University in Israel. Anybody who's familiar with the channel knows that we've talked to several leading theoretical physicists in the past, but this is the first time that we're talking to one that can be legitimately referred to as a quantum engineer. We'll talk about why this matters during our exchange, but for the moment, let me just say that his work as a whole aligns very well with the channel's goal of connecting theory and practice. The theories alone are speculative and they have a place in science, of course, but theory that leads to practice is ultimately what science is all about. And Professor Cohen is at the forefront of this and is a true pioneer, in my view, bridging the gap between many of the mysteries of quantum mechanics that were discovered in the past century and very new practical technology. Again, we'll talk about why this matters in our discussion. Along these lines, Professor Cohen is a member of the Institute for Nanotechnology and Advanced Materials and the Center for Quantum Entanglement Science and Technology, both at Bar Ilan University. On top of that, he is leading a new Quantum Engineering Bachelor's in Science program at Bar Ilan, where he teaches quantum computation, applied quantum mechanics, and applied thermodynamics. Finally, by way of introduction, let me say that Professor Cohen did his PhD on time and non-locality in quantum mechanics under the supervision of two eminent theoretical physicists, Yakir Aharanov and Lev Vaidman. Yakir Aharanov will sound familiar to many of you, previous viewers of the channel, because of his work on the two-state vector formalism, which is central not only to my own work and my own research, but also central to the mission of the channel. So, Professor Cohen, thank you so much for taking the time to talk to us.
Thank you very much for the invitation. I'm glad to be here.
Can we begin with a very general question? I've introduced some of your work, but from your perspective, can you tell us about your academic interests in general and how you got into physics, why physics is interesting to you?
Yeah, sure. I think the introduction was pretty accurate because my research group is called From Quantum Foundations to Quantum Technology, and it reflects my own trajectory in science, starting, as you said, from a master's and then a PhD with Yakir Aharanov and Lev Vaidman, but also the situation in quantum mechanics in which many open questions still seem to require attention, but at the same time, we constantly see new technologies and new practical applications. So quantum theory is highly successful, both on the theoretical and practical side, but nevertheless, there are fundamental issues to be solved. And my group, currently with about 15 members, is trying to tackle both areas. In the fundamental side, we are still interested much in the study of time, mainly using quantum clocks, and also, of course, the two-state vector formalism. We still study non-locality and mainly entanglement and other forms of stronger than classical correlations. We are interested in better understanding the process of measurement and the apparent collapse that we see in experiments, and as well as the classical quantum boundary. We also have some projects on naive approaches to quantum gravity, mainly from a quantum informational perspective. And on the practical side, we work on quantum imaging, quantum sensing, mostly quantum radar-like sensors. And in quantum communication, we work on the security of quantum key distribution protocols, as well as counterfactual communication, that is communication without photons in that transmission channel, at least to some probability. We also work on quantum computation, devising some new applications of quantum walks and trying to better understand the source of quantum speedup from a foundational point of view. I think that these are the main interests. Probably I'm missing some, but yeah, so this is basically what we are doing. And you also asked why I'm interested in physics, or how did I start becoming interested. I think that as a boy, maybe 4 or 5 year old, I wondered about space, about the stars we see in the sky. So I was really interested in astronomy. I took some classes on that. I also read, but as I grew up, I became more and more interested in time and the structure of space, not only outer space, but the space we live in. And then I just took my bachelor's in mathematics and physics and pursued this interest, where quantum mechanics was love at first sight. And since then, I'm fascinated by quantum mechanics.
Very interesting. Well, you cover so much ground, your team. And by the way, congratulations on the 15 members. It's that's a very respectable team. Fantastic. And you cover so much ground there. And you did mention one particular line of interest that I think is especially relevant for us, the two-state vector formalism. Can you tell us about how in the course of your studies, you came across the two-state vector formalism and how you began to work with Yakir Aharanov?
Yeah, I think I was very lucky as a student at Tel Aviv University to hear a talk by Yakir Aharanov. I knew the name, but I didn't know exactly what he works on. And one day, we received an invitation to hear him talking about the two-state vector formalism. And this was mind-boggling, really. I knew quantum mechanics, but not the way that he told it. And I was utterly intrigued. When I looked for a master supervisor slightly afterwards, I could think of nobody else I would like more to supervise me. And although I was a bit hesitant to approach him, Professor Moti Segev and Avshalom Elitzur also helped me to meet him, and then we started working together. From the first meeting, we immediately started writing some joint paper, and we are still working together. He celebrated recently his 90th birthday, and he is very sharp, very fruitful. He has amazing ideas all the time. So yeah, it has been a real pleasure to work with him.
Yeah, that's great. It's very interesting. I agree with you that his work and his ideas are astounding, and I think they're one of my major theses is that his work has very important practical implications for everything that matters to humans. Can you summarize the two-state vector formalism and its role in quantum foundations or maybe in interpretation of physics?
Yes, I can definitely try. So several time-symmetric approaches have been devised, but when we use this specific term, the two-state vector formalism, we usually begin at a 1964 paper by Aharanov, Bergman, and Leibovitz. They were wondering about the time asymmetry that measurement seems to induce. Collapse seems to break unitary evolution, and they wondered whether quantum mechanics can be made time symmetric again, even in the presence of projective measurements. And they were successful in adding a final state to the system in addition to the initial state, and they derived a symmetric probability rule similar to the Born rule, which is usually used for finding the probability of some getting some outcome in measurement, but they did it in a time symmetric way where the initial and final states have equal contributions. Yakir has continued to study this approach, but he wanted to find an empirical way to test the predictions of this formalism. And this is how he came up with the idea of weak measurement. Weak measurement enables us to measure a quantum system in a way which is only slightly disturbing its usual evolution. This way, we can sense the initial state. We can also have some indication related to the final state if we post-select a specific sub-ensemble. And we see that the result of this weak measurement, called the weak value, again depends symmetrically on the initial and final states of the system. And this way we can think about the formalism as composed of an initial forward evolving wave function, as well as a final backwards evolving wave function. And these two together determine the reality of everything that happens in between these two. And this is the customary way of thinking about the two-state vector formalism, although we can also take the final boundary condition, the backwards evolving state, and think about it as evolving forward in time, just like the standard forward evolving wave function. In this terminology, we call the initial state the history state, and the final state, which now propagates alongside with it, we call the we call the destiny state. And there's a recent attempt to formulate all these in terms of operators rather than wave functions. So this is also possible. But returning to the heart of the issue, it's basically an attempt to symmetrize the quantum formalism, utilizing the embedded uncertainty that we see. In classical mechanics, we don't have this freedom. We have some initial state, for instance, of the positions and momenta of all particles, and it determines the time evolution at any subsequent moment in time. But in quantum mechanics, the initial state does not determine the outcomes of all future measurements. And therefore, we have this freedom of adding another boundary condition, completing the description of the system. I think that this is the basic story, and of course I can try to elaborate more.
Well, fantastic. Just to reiterate how astounding and different this approach is, and to summarize for our viewers, please correct me if you think the wording is off, but what is novel here is that in traditional conceptions or interpretations of quantum mechanics, a wave function is conceived as evolving from the past, from the Big Bang, for example, to the present. And what Aharanov has done to explain some of the mysteries of quantum mechanics, and in addition to lead to new breakthroughs in quantum mechanics, is posit a second wave function that complements, in some sense, the forward evolving wave function that comes from the Big Bang with a backwards evolving what you call a destiny state, or a destiny wave function that evolves backward in time from the future. So this combination of a forward evolving and a backward evolving wave function is what makes the two-state vector formalism unique, along with other factors. But conceptually, this is the heart of the matter.
Yes, but if I may, just to tell, the initial state needn't be the Big Bang. The formulation can be much more modest. We initialize the quantum system at a given state. We let it evolve according to some prescribed dynamics. And then at a later moment, we just make another measurement, and then we have a well-defined final state. So in any experiment that we do, we can define this combination of initial and final state. There have been extensions to cosmological scenarios and to the universe itself, but this can be much simpler than that.
Okay, more modest. In other words, yes, more modest. Okay, that makes sense. That makes sense. Obviously, for empirical reasons, it makes a lot more sense to establish more local and more closer in time boundary conditions, right? An initial boundary condition at the start of an experiment, which might be now, and a future boundary condition, which might be in a couple of minutes or a couple of seconds in the future. Okay, that makes a lot of sense. Can you talk about, well, prior to this question, allow me to remind viewers that of the role of interpretation in physics. And here I'd like to cite the work of Richard Feynman, Nobel Prize winner, of course, in physics, who in his famous lectures at Cornell University talked about the role of interpretation and how a good physicist keeps as many possible equivalent interpretations of physics in his mind, because he or she never knows which one of those interpretations is going to lead to the next breakthrough. So can you talk about some of the breakthroughs that this new approach to quantum interpretation has led to? Some of the empirical advantages of this.
Yes, sure. I really like this quote of Feynman. And indeed, in our works, we sometimes use the ordinary Copenhagen interpretation, but sometimes we use the Bohmian interpretation, Bohm-de Broglie, pilot wave. We use the hydrodynamic Madelung approach. And in one work with Vaidman, we also thought about it in terms of the many worlds interpretation. So I really agree with this, bearing in mind that interpretation should explain what we see, but it should give as predictions all the things, all the observations that we have. It cannot deviate from them. Nevertheless, the two-state vector formalism has been very helpful for conceiving new ideas. And I can give several examples. Weak measurements that we discussed were born inside or within the two-state vector formalism. They can be thought of as a tool or as an offshoot of the formalism, but by now they are very interesting and helpful in their own rights. They are not only a tool, they are a subject of research in themselves, with many experimental demonstrations employing weak measurement in order to enhance the precision in quantum sensing. So weak measurements were inspired and gained a lot of understanding from the two-state vector formalism. This is one example. Another one, which is somewhat related, is the phenomenon of super oscillations. Super oscillations, described as such by Professor Sir Michael Berry, relied on some idea that was developed in Tel Aviv, according to which when you prepare a photon in a box having several possible frequencies, you can get upon a particular post-selection an ultraviolet photon outside the box. So super oscillations describe a surprising scenario where a function oscillates faster than its fastest Fourier component, at least in some small region of space and time. So this is another example of major interest nowadays. Quantum walks were also conceived using the intuition from weak measurements and the two-state vector formalism. And many quantum paradoxes showing us just how quantum mechanics is intriguing and different from classical mechanics. And I think that it's very constructive that many of these proposals have already been realized in the lab. They were demonstrated in photonic systems, but also with atoms, neutrons, with superconducting qubits, with trapped ions. There were many physical platforms which realized these theoretical ideas stemming from the two-state vector formalism.
Okay, very interesting. Thank you. Well, given this empirical fruit of these two-state vector formalism, and in light of your very interesting work with Lev Vaidman and Yakir Aharanov, who have, in some sense, conflicting takes on the two-state vector formalism. Yakir Aharanov interprets the two-state vector formalism in one way, using a certain language to describe it, and Lev Vaidman objects to that language and prefers the many worlds interpretation, which to me just doesn't make a lot of sense. But obviously Lev Vaidman is a well-respected physicist, and he has his reasons to interpret it in terms of the many worlds. So in light of this conflict and your work with both of these gentlemen, can you elaborate on why there are skeptics to Aharanov's approach to the two-state vector formalism?
Yes. I can definitely say that doing my PhD with both Aharanov and Vaidman was surely interesting. As a student, I had the rare task of writing a comment with one of my supervisors against a paper by the other supervisor. So it really happened, and I think that Vaidman promoted it. He always promotes controversy if the purpose of this controversy is better understanding things. So indeed, Vaidman sees the two-state vector formalism, or the final boundary condition, as some epistemic addition. The basic ingredient is the wave function, the forward evolving one. And we can add to this description just an additional information once we know the final state. But I think that Yakir Aharanov sees this issue in a deeper sense, and he believes that the future is there, but we can't reach it yet. We don't know about it, and therefore we have free will to act as we want. But fundamentally, the description is symmetric, and he also believes, that is, Aharanov believes, that the description should not be based on the fundamental level on wave functions. Wave functions are helpful as a mathematical tool. They simplify calculations, which are otherwise hard to perform with operators or matrices like Heisenberg wanted. But to really understand what quantum mechanics is about, Aharanov tries to promote now an operator-based approach. And I think that for traditional reasons, due to Schrodinger's works and the way that we were used to think about quantum mechanics, perhaps some people prefer to use wave functions, just the ones coming from the past, because in most cases we don't know what the post-selected state would be, so people prefer this way. And maybe not everyone agrees that you can accommodate these two. I mean, the final boundary condition and a dynamical notion of time, as well as a sense of free will, which has to be carefully defined. But I guess that for people, when you have not one, but two boundary conditions, reality may seem highly constrained, which is not necessarily a bad thing, but maybe it negates some other views. And another point of contrast between Aharanov's and Vaidman's views is related to the notion of locality. Vaidman believes that everything should act in a purely local way, and description of physics should be allowed by fields, by forces, while Aharanov, from his famous work with Bohm, believes in the importance of potentials, of what he later called dynamical non-locality, where you can have equations of motion in which observables here depend on something far away over there. So they have conflicting views about locality. Aharanov believes in non-locality on a very fundamental level, while Vaidman is sure that everything should be described only or not only, but fundamentally in a local way.
Allow me very quickly to make reference to the Aharanov-Bohm effect, which Yakir Aharanov co-authored with famous physicist David Bohm, and which has had an absolutely extraordinary impact on physics, on theoretical physics. There's entire conferences and scheduled around this and to celebrate this work. It was so surprising when it came out, and here we are many decades later, and it's still producing some very interesting outcomes on many different levels. what's surprising to me about Vaidman's approach is that he prefers the many worlds interpretation, and viewers will see this as repetitive on my part, but the many worlds interpretation has a difficulty that, number one, it can't be tested. Number two, it doesn't say anything relevant about this world, the one that we actually live in. So that seems like a major objection that I would like to ask him about. In any case, very, very interesting topics being covered here. And there's so much that you say. Almost every sentence you say takes me off on a different tangent and a different question. But allow me to come back and make reference to a very fascinating lecture you gave some years ago at the Perimeter Institute on a final boundary condition to the universe. Reflecting back on that lecture, can you share your experience, that particular lecture, whether your thinking has evolved since then, whether you've made any progress along these lines?
Yes, of course. As far as I recall, the lecture had two contributions related to the importance of a final boundary condition. One of them was a joint work with Yakir Aharanov and other students. And the other was related to the final state conjecture in black holes as a means of information to escape. We didn't conceive this idea, but we studied it. And the main idea was actually motivated by the conflict you mentioned with the many worlds interpretation. What we looked for, mainly Aharanov, was a way to restore time symmetry, even at the level of the whole universe, without invoking many worlds. The many worlds interpretation seems time symmetric because everything evolves unitarily. There is no collapse, so you can take everything, all these branches at the future, and just return the way you formed them. But as you mentioned, there are other apparent problems with this interpretation, and we wanted to show that we don't necessarily have to use it. We can have a single branch universe, and we can create in this branch an effective notion of collapse thanks to a final boundary condition on the universe as a whole. So this scheme that we call the two-time decoherence scheme is based again on the combination of initial and final boundary conditions. And in an attempt to postpone collapse until we reach the final state, we just use the standard unitary evolution, where at each instant of time when we make a measurement, the outcome is determined by both states, and the final state is robust enough such that it can survive all these subsequent measurements. It stores information in a very robust way, which can be evolved backwards to the beginning of time and determine alongside with the initial state everything that needs to be known. In one instance, we describe it as a hidden variable theory in which the hidden variable already knows what we are going to measure and is determined in the future state. So all outcomes are encoded there in the final boundary conditions, and they help us understand why we see certain outcomes rather than others. It can also explain to some extent the boundary between classical and quantum mechanics upon coupling to a large macroscopic system. It explains what macroscopicity is. So this was, I think, the main takeaway from that talk, which we then continued to develop since then with subsequent publications. But still, there are many problems there and many points to address and improve in this interpretation of measurement and collapse.
Okay, well, thank you for sharing that. One thing that I've never heard, I've heard several objections to the two-time approach, and including one by David Albert, responding to a lecture by Aharanov. One thing that I always wonder about is why Aharanov or his the members of his team do not talk more philosophically about the work. Is this something that has to do with what is acceptable in theoretical physics, or why do you think that a more philosophical approach is not taken? For example, in fact, David Albert, who's a philosopher and a theoretical physicist as well, or trained as a physicist, one of the things he objects to the Aharonov's ideas is the notion that philosophically doesn't make much sense, right? To think of the future having impact on the present. However, one thing that I immediately respond to this is, wait a minute, at the beginning of philosophy, Aristotle posited a final cause to reality, or a final cause to the way we understand the various causes, right? And why is this never talked about in this context of physics? Do you have any opinion about this?
Yeah, I think it's a good question. I personally have much admiration to philosophers and philosophers of science. In particular, I go to conferences on the philosophy of physics, and I think that this is highly desirable, that more people would try to address the philosophical questions raised by the two-state vector formalism and weak measurements. And there are, I know of excellent philosophers of science addressing the notions of weak measurements and the two-state vector formalism. Within the Aharonov school, I think it's mostly Vaidman, who publishes philosophical papers in philosophical journals. He has more interactions with philosophers of science. But I don't think, at least from my point of view, that there's a deep reason for that. It just happened that I was drawn more to applications and practical consequences, and other prominent researchers working with Yakir, such as Sandu Popescu, have their own interests, for example, in quantum information and non-locality. So this is all I know about that.
Okay, well, thank you for sharing that. Our time is coming here to a close, and we have so many other questions I would love to talk about, but allow me to make a transition to your current work on quantum computing and the various fields that you're working on. One area of particular interest to us and to the channel are the connections between your work and the practical impact of the research and the areas that you're taking your work. Can you comment on this? What do you think are some of the most interesting prospects for the future?
Mm-hmm. Yes, this is a big question. So first, I strongly believe in the employment of mathematical tools of quantitative analysis. But together with this toolkit, Aharonov always emphasized and emphasizing the importance of having a good question, a good physical question, and a good physical intuition towards this question before even doing the math.
This is so profound. I'm sorry to interrupt, but this is so profound. Every time I hear him say this, I can't agree more with him. I think it's so important and so so true, so relevant. I'm sorry.
Yeah.
Please continue.
Yeah. You are right. He is very profound, and I think this may apply to other fields of research and science, even social sciences. I also bear in mind the importance of uncertainty. During the last few years, I'm trying to advance the view according to which quantum uncertainty might be the most fundamental property of quantum mechanics. Any phenomenon that I see, any quantum phenomenon can be traced back to quantum uncertainty or to non-commutativity of observables. And I see uncertainty as an enabler. This gives us freedom to succeed in various tasks. For instance, quantum key distribution that I mentioned relies on quantum uncertainty for being secure. And also when we analyze quantum algorithms, when we analyze quantum computation, we see that the non-commutativity, which is a quantum property, the fact that once you do one act, it cannot be replaced with another act coming afterwards without changing the result. The order matters when you do actions in quantum mechanics, usually. So uncertainty is both a fundamental property, but also a vital resource that we are trying to work with. As another example related to what we are doing, in quantum light, and also with matter, there's the notion of squeezing, where we try to squeeze the uncertainty in one parameter, paying with the increasing the uncertainty in another parameter. And so all these manipulations with uncertainty might also apply to some extent when we think about classical uncertainty. I tend to think that classical uncertainty is also a fundamental factor to take into account. We need to try to know what we don't know. And of course, there are the things we don't know that we don't know, but all of these affect what happens. And so it's better to control them the best we can and adapt to these uncertainties. And finally, there's the final boundary condition, which philosophically tells us that we needn't forget about what's coming next, or we don't necessarily, we can't rely solely on the past. We have some destiny in the language of quantum mechanics waiting for us. So it's not a scientific explanation, it's just wishful thinking to keep in mind the future, to think more about the future and not only about the past. And often in quantum mechanics, once we see the post-selected state, once we succeed in the post-selection, we can go back and interpret what happened in the past. We have a richer notion of reality using the weak values, for instance. And also, I think this happens in life once we reach the future, we can reinterpret the past, but the future is unknown to us, and all we can do is act freely the best we can. But this is not science, just some philosophical thoughts.
Well, allow me to respectfully push back on this idea that it's not science. We recently talked to Michael Levin, a synthetic biologist pioneering work in his field at the University of Tufts. And he respectfully disagrees with this notion because he uses precisely this framework of a future impact on time evolution to make the breakthroughs that he's been able to make. So one thing I've argued since talking to him and before is that it's not only philosophy, it's actually practical, it has practical implications for how science is carried out. And he is very respectful, of course, and he challenges people who object to him using words like goals and purpose. He says, listen, these are words that we use because they have a direct and powerful impact on how we set up our experiments and how we carry out our science. If you have a better approach, bring it on. We're very interested. But for the moment, we are regenerating animal limbs using bioelectricity and using this framework. So once again, I'd like to just respectfully remind listeners that this approach is actually, I think, more than philosophy. It's very, very profound on almost every level. And the work of Michael Levin is demonstrating this to be the case. Not to mention our own experience with goals and how the future evolves according to the goals that we might set for ourselves on a just basic psychological level.
Yeah, I didn't want to sound disrespectful to this work, which honestly I don't know enough. It's just not the quantum science that I do at the moment. So I don't have quantitative analysis of this. And in fact, any such effect of the future on the past has to be carefully analyzed in order to prevent violations of causality. So these terms are really subtle, and it's very hard to escape the current paradigm. But we know.
Am I mistaken to think that in some sense the two-state approach is a legitimate equivalent approach to all the others, whether the Copenhagen or whether the
it's mathematically equivalent.
Is mathematically equivalent. Okay, it's the conceptual interpretation that some people don't like or object to, but it's conceptually it's perfectly viable. Going back to what Feynman recommended of physicists to being open to any number of different interpretations because they never know where the next breakthrough is going to come from.
Yeah, that's right. That's right. I again emphasize that I cannot borrow, I cannot reach consequences from this approach to macroscopic systems, to social sciences, for instance, to biological systems. I just cannot use the quantum results in the microscopic world and transcend them this amount. But what I meant to say was just taking the state of mind, the mindset of a time symmetric view, which might be helpful as a tool. Again, this is what I can prove. I can prove results in quantum mechanics. I really don't know about biological systems.
That makes sense. You want to be conservative as a scientist, and that makes absolute sense. Okay, last question, if it's okay. you're working on quantum computing, and of course, in quantum computing, the concept of error correction. You've made the connection between error correction and the holographic principle, or the ADS CFT correspondence. Can you quickly elaborate on this?
Yeah, I think I was citing a famous paper by Almeri, Dong, and Harlow from 2015. Intuitively, I think that they try to account for the robustness of space-time and to explain how the bulk properties are generated using a scheme resembling quantum error correction, because similarly, quantum error correction is used in order for quantum information to be more robust against noise and errors. So it was suggested in a highly intriguing and really amazing work that maybe the structure of space-time itself, which may well be quantum at its origin, sustain itself through quantum error correction code. And this is done through the ADS-CFT correspondence. But this is not my idea.
Okay, very interesting in any case. But the connection to that and between quantum, does it have an impact on any of your current research in quantum computing?
Yes, we are also studying some error correction mechanisms. In our case, it won't come as a surprise that we are trying to use weak values and weak measurements as a way to better tolerate noise in sensing, communication, and computation.
Fascinating. Well, Professor, congratulations on your work, and thank you for your work, which is so interesting and fascinating, and I think important for everything that matters to all of us. As a final note, can you say something about, are you receiving people into your programs, or where can people follow your work?
So the undergraduate program that you mentioned begins now its third year at Bar Ilan University, and students are most welcome to join it. My research group is reaching some, is approaching its bounds, but I'm always happy to interact and interact with researchers and consider new applications. Yes, more information perhaps can be found on my website at Bar Ilan.
Fantastic. Well, thank you very much once again for taking the time to talk to us. It was a real honor and a pleasure.
Thank you very much.